Chapter 8, Discrete Random Variables. Now we are going to learn how to use the property which is the sum of all probabilities add up to 1. Look at the description. For a discrete random variable, the sum of all the probabilities must add up to 1. In both example 3 and example 4, the sum of all the probabilities was 1. This is example 3. Here we have rolling a die, and in example 4 we have tossing a coin. As you can see, for each one we have a probability distribution. Let's add all the values for example 3. 1 over 6 plus 1 over 6 6 times is equal to 1. The same applies for example 4. 1 over 8 plus 3 over 8 plus 3 over 8 plus 1 over 8 is equal to 1. Thus, to be sure of the probability distribution after constructing the table, we should add the probabilities and their sum should be 1. We can write this in a simpler way by using the notation for the summation. So summation P of x, or summation of capital P of capital X equals x is equal to 1 for all the values of x. Remember to always write lowercase p for the random variable and to use the capital P when capital X equals to x. So the value of the random variable is equal to a specific value. In both cases, the summation is equal to 1. Look at this example. A tetrahedral die has the numbers 1, 2, 3, and 4 on its faces. This is a tetrahedral die. All the sides for it are triangular. That is why we have 4 faces and not 6. We used to work with the cubic die which had 6 faces. The die is biased in such a way that the probability of the die landing on any number x is k over x, where k is a constant. Here we have the word biased, which is opposite to fair. Fair means when the die is thrown randomly and any number can result, so the probability is equal for all the faces. However, biased is opposite to the word fair. That means we are throwing it in a way that causes the probabilities not to be equal. The probability is k over x. Find the probability distribution for x, the number the die lands on after a single roll. We need to construct the probability distribution table. This is the table. Here we have x, the values of the random variable. We already know they are 1, 2, 3, and 4. Probability of capital X equals to x. We know that each value is k over x. So when x equals to 1, that means k over x is k over 1. So we write it like this. When x is 2, k over x is k over 2. When x is 3, we have k over 3, and when x is 4, we have k over 4. To get the probability distribution, we need to know the value of k. To calculate k, we use the property that all these probabilities are equal to 1. So we write, to find k, use the property summation of p of x, or summation of capital P x equals x. Both are all values of x, and they are equal to 1. That means for x equals 1, it is k over 1 plus, for x equals 2, k over 2 plus, for x equals 3, k over 3 plus, for x equals 4, k over 4. The summation for all of this is 1. Now we have an equation with one unknown, and the common denominator is 12. 12k plus 6k plus 4k plus 3k over 12. All of this is equal to 1. Let's add all the k's. We will have 25k over 12 equals to 1. Now we cross multiply. The answer is 12 over 25. So k is 12 over 25. We calculated k by using the property that the summation of all the probabilities for the value of x is equal to 1. Here here we have the table. For k equals 12 over 25, that means k over 1 means 12 over 25 over 1. So 12 over 25. Now for k over 2, we have 12 over 25 divided by 2 over 1. We solve this like this. So 12 divided by 2 times 25. The value is 6 over 25. Okay, now 12 over 25 divided by 3 over 1. We multiply the ones far away together and the close ones together. 12 over 3 times 25. The answer is 4 over 25. Finally, we have 3 over 25. This is how the final table will look like. This is the probability distribution table for x. We calculated the probability for each random variable. Pay attention that we said that the die is biased, so the probabilities are different for each value.